Hi there, and welcome to Chapter 2.7 from Stevens' Matrices, Vectors, and 3D Math. In this chapter, we're going to talk about collision detection between a line and a plane, and then the appropriate bounce response. For example, if this is my plane, and I have a line coming, and it hits there, right? It would have gone to, say, here. I want to find out where does it hit, where is that little X, and if you were to get a bounce, where would it end up? Right? So, we're talking about lines and planes here. And so, in order to look at our first problem, where does the line hit the plane, we're going to be talking about the intersection of a line and a plane. So let me put this into full screen mode. Okay, the intersection of a line and a plane. And by the way, this is really easy to do if you think about it geometrically, right? Up here I have a line. It's going from here to here, right? And there's an x as a function of t, y as a function of t, and z as a function of t. I want to find out when x, y, and z satisfy the equation for this plane. So for example, if this is my line, right, there's an x function, a y function, and a z function. And this is my plane, which contains an x, a y, and a z. So all I need to do is take my expression for x and put it in here. My expression for y, put it in there. My expression for z, put it in there. All right, and so that's what I've done in this second equation. Right? And so now I just want to solve for t. And at t, whenever I solve for that, that'll give me the time of intersection. Not really the point, but the time with respect to moving along this line. So you just distribute your 3, distribute your 2. Well, it's not really distributing. Multiply your 2's in there. And then you want to collect your t's. So I have 8t minus 3t is 5t. And then I have negative 18 and positive 3, so it's negative 15. Add 15 divided by 5, I get t equals 3. And notice that is not a point in 3 space, that is a time. Right? That's why it says it here. I mean, time in sort of the extended definition of what time is. Here it's just another parameter. The point being, if I take t equals 3, and I put it right into these equations, I will get, let's see, if I let t equal 3, x will be negative 2, y will be 12, and z is always 9, so it will stay 9. So that's actually where this line hits the plane, is at negative 2, 12, and 9. Right? So it's a pretty easy process. You just take x, y, and z and stick it in there, there, and there for the plane and solve for t. That gives you your time of intersection. Plug that back into the parametric equations for the line, and that'll give you your point. If you want to do this with software, like something like MATLAB, you can do it. If you break this all into x, y, and z in terms of x equals x1 plus at, y equals y1 plus bt. If you play that same game and then you get some more, you have to create some variables here, e, f, and g maybe. Plug everything in, do everything symbolically without any numbers, and you have just variables. You can do this, and you can solve for t, and you get a solution that looks like this. Right, where this piece of p is a point on the plane, this piece of L is some point on the line, this n is the normal vector to the plane, and this v is the direction vector for the line. And this is by no means a shortcut if you're doing it by hand. If you're doing it by hand, and I can't say this strongly enough, do this process. If you're doing it by hand, you want to just go through the process described here because it's actually easier. If you're doing this inside of a machine, then you can go with this formula here. There's a lot of multiplication and addition, lots of places to go wrong in this particular formula. But it is worth pointing out that, every time you have a formula and you're going to put that into a machine, if n dot v is 0, you've got a problem. But if n dot v equals 0, that means the normal to the plane is orthogonal to the line that we're talking about. And in other words, the line is parallel to the plane. So there might not be a point of intersection. In fact, there won't be unless the line itself is sitting in the plane. But if that's the case, then this one will be 0. Right? So there's a little bit of checking you have to do if you're going to do this in a machine. If you need to do it by hand, do this procedure. Don't use the formula here. And by the way, once you do solve for t, you can find that point of collision by taking t times the direction vector on the line, adding it to that point from the line. All right. Okay. So, for example, we're going to we just found this point of intersection, right? For this line. So for this line right up here in this plane, we found this point of intersection. So I'll clean out some of this red so that it stands out. The point I'm talking about is right here. So we went through this process. It was pretty quick, pretty easy, pretty fast, and we got this collision point between the line, or the intersection point between the line and the plane. All right, and so just to demonstrate that this formula would actually work, if I wanted to use this formula on this plane and this line, well, the first thing I'd need is, n would be normal to the plane, so that's going to be 3, 2, negative 2, 3, 2, negative 2. I need a point on the plane, and a point on the plane, there's infinitely many, but the easiest one is if you let x equal 0, let y equal 0, that means z equals 0. So that point on the plane is just 0, 0, 0. Right? A point on the line, well, let's see. Now I have to go to my line. I just have to find one point. Well, if I let t equal 0, then I get the point 1, 0, 9. And so that's where this point on the line comes from. All right. And I think we've got everything. Oh no, we need the direction vector for the line. So the direction vector for the line is just negative 1, 4, and then a 0. So now we have all of our parts, right? Negative 1, 4, 0. So look, getting all these parts correctly without errors is tricky enough. Then you have to do all the addition and subtraction. And so what I need up here, so I have n, I have v, I have p, the point on the plane, point on the line. I'm going to get the vector of the point on the plane minus, so that's really the vector from the point on the line to the point on the plane. So that's right here, negative 1, 0, negative 9. And if you go through all that, you're going to take n dotted with this vector right here. It's going to be negative 3 plus 0 plus 18. Right? And then that's going to give you 15. And then on the bottom, you're going to take n dotted with v, which is right here. It's going to be negative 3 plus 8 plus 0. And that's going to be 5. So the time of intersection, once again, as found by that formula, is 3. Risky, though, because there's an awful lot of work going into that. And then if you take 3 times the direction vector and add it to the point on the line plus 3 times the direction vector, it actually gets me the same point of intersection. Again, it's tempting to use this formula because it's a straight-up formula, and this is more of a process. But the process, if you're doing this by hand, is so much easier than the formula. Okay, so once we actually get a collision point, right? Suppose I want to go from M to Q. That's my line. We'll call it a directed line segment. But I hit the plane here at point P. So the first thing I do is determine point P, and now I'm going to do a bounce response. And there's a couple of properties of this bounce response. For one thing, so this will be where this was sort of the bounce vector, right? And it's going to have the same length as PQ. So PB is going to have the same length as PQ, meaning I'm not losing any energy on the bounce. As far as I would have gone in this direction is the same distance I will go only now in this direction. And I'm going to require that my bounce, when I hit the plane, the angle that I hit the plane is the same as the bounce angle. Right? These two are the same. Okay, and so to do this, it isn't really bad. It looks a little messy here, but there isn't much going on. So the first thing I'm going to do, I have my plane. I'm going from M, I hit at P, and I want to get basically PQ to bounce up that way. So the first thing I'm going to do is I'm going to take a look at this normal vector, right? And if I take this normal vector and I project if I project MP onto the normal vector, that's going to give me basically this vector right here. That's the projection of MP onto my normal vector. But I actually want it to be going the other way. I want it to be going up like this. So I just take the negative of that. It's now going up. So this is now the negative of the projection of MP onto N. You could think of it as the projection of PM onto N. All right, and so I'm going to go up 2 of those. 1, 2. Right? And so what happens here is what I want is this vector PR, right? And so what that is, and it's the same thing as this one over here, right? This is going to be MP plus, so if I start here, I go MP plus one of those, which is a minus projection MP onto N, minus another one. That gets me the vector I want. And so what's worth pointing out is I wanted this angle to equal this angle, right? Well, if you notice this angle, so I'm going straight across this projection from M across the normal to R. That's parallel to this plane, right? So this line here is parallel to this line here. And so what I get is that this angle here is going to be equal to this angle here by alternate interior angles from geometry, right? And then I know I went up the same distance here as I did here, so these two angles are the same, and this angle are the same. So I basically have the angle that I hit is the same angle that I bounce. Okay, so what I have now is PR, which is sort of the bounce vector, but it doesn't necessarily have the correct distance, right? I want it to have this distance. Looks like it's coming up a little short here, but it might come up short, it might come up long. It's hard to say. But once I have PR, I just want to have the length of PQ. And that's easy to do. I just take PR, I divide by its length, so now it has length 1, multiply by the length of PQ, and now it has the length of PQ. So now I have my bounce vector, which I call PB. Right, that's this thing right there. But to actually get my bounce point, I have to take my point of intersection, or my point of collision, and add the bounce vector. It's a popular last step that people forget. You got to make sure that the bounce vector is added to the place where you actually hit. Otherwise, your bounce vector might, be somewhere down here, and it doesn't end anywhere near where the actual projectile or ball might land. Okay, so let's do an example. Next page. So let's see, I'm going to have this plane, and I'm going to have this line. Well, we won't even do this line first, but we'll say that we have this plane, and a ball starts here at M, all right, and it wants to go to Q. So what I have is, just to do a little picture, if I'm at M here, M, and then I want to go to Q. All right. Okay, so the first thing I need to do, and what I want to determine is, where does this bounce end up? Where's my point B? Right? So the first thing I need to do is define my line. Like, I want to find this point of intersection, right? That's the thing I called P. Point of intersection. So I need to build that line. But that line goes from M to Q. So the direction vector is just going to be MQ. Right? So if I take Q and subtract M, it's going to be 0 minus negative 6 is 6. 0 minus 0 is 0. Negative 5 minus 15 is negative 20. So that's my direction vector. And we're going to start at M. Alright, so I have M and a direction vector, which I used to call V. So it's going to be negative 6 plus 6t, then 0 plus 0t, and then 15 minus 20t. Right? So that gives me my line that's going to go from M to Q. Technically, that happens when t goes from 0 to 1. Right? So I want to know when it hits. Specifically, I want to know where it hits, but when it hits is what I'm going to solve for. So basically, I take my x, my y, and my z that I just found here, this x, and I'm going to plug it into that x for my plane. This y is going to go into this equation for my plane, which doesn't make any difference because there's no y in there. And then this z is going to go right there. Right? So the y actually doesn't even show up anywhere. And when I do that, there's my x plus z minus 2 equals 0. That's this equation right there. So then I have a 6t minus 20t, so that's minus 14. I have a negative 6 and a positive 15 is 7. Sorry, negative 6, positive 15 is positive 9, minus 2 is 7. And I solve this for t, and I get t equals 1/2, but that is not my point of intersection, that's my time of intersection. So I take t equals 1/2, I stick it in there and there, and so I get the point of intersection is, let's see, negative 6 plus 3, negative 3, 0, y is always 0, and then 15 minus 10 is 5. So I found my point of intersection. Right? And then my bounce starts by finding PR. This was the PR. Right? I basically got the bounce direction, but I had the wrong distance. So I have to take MP, right? There's M up here. There's P down there, so I basically take P minus M, so that's negative 3 minus negative 6, it's positive 3, 0 minus 0, 5 minus 15, negative 10. I'm going to subtract 2 of these projections of MP onto N. But MP onto N, where is my N? Oh, N was the normal from the plane. So you have to get N, the normal to the plane, is 1, 1, negative 2. And remember, those are just staring at you in the equation. Oh, wait, not 1, 1, negative 2. My fault. It's the coefficient of x, which is 1. The coefficient of y, there is no y, so it's 0. And the coefficient of z, which is 1. I'm running out of space up there. So there's my normal, 1, 0, 1. All right, so I do the dot product right there. I divide by n, the size of n squared, times n. There's a whole lot of math here that is certainly better done with a machine, but if you're very careful, you get PR equals 10, 0, negative 3. And that's just about 20 individual multiplies and adds. So again, something worth doing on a machine, but if you do it correctly, you get some nice whole numbers because the problem was rigged to work out that way. But this just gives me PR. That doesn't give me the right distance. So this is the correct direction of my bounce. That's almost there. I want to get the correct distance, and that distance is PQ. So I take PR, the vector PR, divide by its length, so now it has length 1, multiply it by the length that I want it to be, and it now has the correct length, correct distance, and it turns out that PQ and PR in this specific example are actually the same length. So they cancel out and I get 1. So this is purely coincidence. All right. In this case, PB equals PR. That is a coincidence. That won't always happen, right? So that gives me my bounce vector, which in this picture down here is this green vector here. But you have to remember to add that vector to the point of collision. When you do that, you get 7, 0, 2, which represents this final resting place for the ball. Right. That's where it ends. This vector here, the green vector, is basically the bounce vector. And if you want to do this in, oh boy, let me turn this off. Okay, nothing like a cell phone interruption, but I'm so close to the end I don't want to start this over. Okay, so you get your terminal point on the bounce vector, and it works like a charm. And if you want to play around with this, there is a program called Plot Bounce Plane in the Chapter 2 program repository, and you should pull that out and play around with it, because it has some, it basically shows you how to do this process in code. It's easy to do. It's actually this problem exactly in MATLAB code. So pull that up, play around with it, make sure it makes sense to you, and I will see you in, this wraps up Chapter 2, I believe. All right, well, congratulations, a whole chapter down, and we will start Chapter 3 in the next video. Bye now.